low phase noise, high bandwidth frequency synthesis techniques. Fractional N synthesis. Frequency synthesis is an essential technique employed in RF systems to achieve local oscillator low generation or direct modulation transmission. Fractional N synthesis offers the advantage over integer N-based systems of decoupling the choice of synthesizer resolution from its bandwidth. Fast settling, high-resolution synthesis becomes possible, giving greater design flexibility at the system level. Fractional N synthesis can be separated into two categories: classical fractional N synthesis and sigma delta fractional N synthesis. The trade-offs associated with the different types of fractional N synthesis and show that the key constraint limiting the bandwidth of modern synthesizers centers around management of fractional and quantization noise. Quantization noise is introduced to the synthesizer as a byproduct of the fractional and the ring process, and so is unavoidable. After examining existing techniques aimed at lowering the magnitude of quantization noise, propose a synthesizer architecture that overcomes the core limitation of this prior work, namely achieving a high-quality gain match between the quantization noise and cancellation signal. 29.1 The issue of fractional and quantization noise. The classical approach to fractional and synthesizer design employs ditto ring and phase interpolation, as depicted in Figure 1:1.3. An accumulator carryout signal is used to ditto the control input to a multi-modulus divider such that a fractional average divide value is obtained from a divider that supports integer values. The digital-to-analog converter DAC is used in conjunction with a phase accumulation register to cancel out periodicities in the phase error signal, ET. These periodicities represent quantization noise introduced by the fractional and the ring process. The main performance limitation of this approach centers around the difficulty in creating a precise match between the noise cancellation DAC output and the phase error signal. In sigma-delta fractional and synthesis, the most popular technique used today to generate fractional divide values 4 to 9, the spurious performance is improved through sigma-delta modulation of the divider control. The quantization noise introduced by ditto ring the divide value is therefore widened and shaped to high frequencies, such that it is substantially filtered by the synthesizer dynamics. In order to obtain sufficient randomization to reduce spurs to negligible levels, sigma-delta modulators of order 3 or higher, often employing LSB ditto ring, are often employed, necessitating a higher order loop filter to counteract increased noise slope. The shaped quantization noise can easily 30 sigma-delta fractional and synthesizer and noise bandwidth trade-off dominate at high offset frequencies, introducing the noise bandwidth trade-off, which translates to low closed-loop bandwidths for low-phase noise synthesizers. Depicted in Figure 1:2, this trade-off is the bottleneck preventing high-bandwidth fractional and synthesis, and therefore presents an obstacle to achieving the central goal behind fractional and synthesis, which is to increase synthesizer bandwidth. Bandwidths reported in the literature for sigma-delta synthesizers are typically below 100 kHz for high-performance applications. 8.10-14. 1.2 Prior work aimed at reducing fractional and quantization noise to approaches have emerged to improve the noise bandwidth trade-off. The first involves reducing the quantization step size of the divide value ditto ring action through the use of multiple VCO or divider phases 15 to 17. Introducing multiple VCO phases is the ideal means by which to reduce the quantization step size. To explain, phase is the system parameter on which a PLL operates, so choosing one of a number of finely spaced VCO phases to clock the divider directly translates to a reduced 31 quantization interval. In a similar manner, multiple divider output phases may be created, though it is still necessary to space these phases by some fraction of a VCO period, since the VCO period is the fundamental quantization step size in the system. In practice, the number of VCO or divider phases that can be accurately generated is limited. Phase resolution is often set by a gate delay which, for high-frequency outputs, can be a significant fraction of the VCO period. Additionally, to generate multiple phases, either ring oscillators must be used, which have inherently poorer phase noise performance than LC oscillators, or a DLL with all of the associated overhead must be employed. 17. Mismatch between the phases occurs and must be carefully dealt with. Very recently, a modification has been proposed to the selection logic used in the multi-phase approach of 15. In this case, Very high-order sigma-delta modulation is applied to the phase selection mux in order to make each tap equiprobable in a histogram sense. 18. For the simulated synthesizer proposed in 18, the 7th order sigma-delta modulator was used to randomize the selection of output phase for a 16-phase divider. Noise shaping of this order requires large numbers of extra poles in the loop filter to counteract the increased noise slope of the high-order modulator. Additionally, the multi-phase approach is ultimately limited in its ability to reduce broadband phase noise by limitations in creating the delay. The second approach to reduce the noise bandwidth trade-off uses a DAC to cancel the error signal. 19. 20. This method builds on the idea behind phase interpolation, but introduces sigma-delta design techniques to reduce the impact of DAC nonlinearity. The main limitations with this architecture center around achieving a good match between the DAC output and phase error signal. Matching these signals is difficult because they are processed by separate circuits whose outputs are summed. An additional limitation of this technique is that a high-resolution DAC is required to achieve high levels of noise cancellation. In 19, a 4-bit coarse DAC and 4-bit fine DAC were used, resulting in 16 decibels improvement in broadband phase noise and 45 dBc fractional spur levels. A similar approach proposed in 20 results in 15 decibels noise suppression and 60 dBc fractional spurs for a 5-bit cancellation DAC. 32. An alternative approach that utilizes a DAC to reduce quantization-induced phase noise is proposed in 21. The separate phase detector and DAC circuit elements are replaced by a hybrid structure, which we'll refer to as a PFD/DAC. By embedding the two functions into one circuit, an intrinsically better gain match between the phase error and DAC cancellation signals is obtained. However, the architecture presented in 21 does not address the issue of mismatch between unit elements of the DAC, or between the timing signals in the phase detector, which will result in incomplete phase error signal cancellation and spurious feed-through. While all of the proposed techniques described above succeed in reducing broadband phase noise levels by effectively reducing the phase quantization step size, their performance is limited by mismatch between the quantization noise and the cancellation signal. 1.3 Proposed quantization noise reduction technique to reduce fractional N quantization noise. Propose the architecture shown in Figure 1-3. The proposed synthesizer leverages advances in noise shaping DAC design to ease the requirements on the cancellation DAC used by the traditional fractional N approach. It utilizes a PFD/DAC structure to obtain a good intrinsic gain match between the phase error and DAC cancellation signal. However, this work makes the key contribution of introducing techniques to minimize the impact that PFD/DAC mismatch sources have on phase noise performance. Indeed, matching issues create the bottleneck in previous approaches since they result in error feed-through that is manifested in the phase noise spectrum as large spurs, or increased broadband phase noise. The proposed architecture incorporates several digital signal processing techniques to reduce the impact of non-idealities that occur in the PFD/DAC such as unit element mismatch, timing mismatch, and any residual gain mismatch occurring between the PFD/DAC output and phase error signal. The key issue with prior fractional and synthesizer implementations is that the cancellation DAC output and phase error signal are poorly matched. This error is a direct result of the fact that separate circuits have been used to implement the two required blocks. Figure 1-4 depicts the proposed PFD/DAC structure, which greatly reduces mismatch between the two signal paths. The proposed PFD/DAC differs from a prior implementation of a hybrid phase detector/cancellation DAC scheme in that it compensates for mismatches within the PFD/DAC structure itself. As will be discussed, mismatch between magnitudes of the phase error and cancellation signal and timing mismatch between signal paths in processing phase information is a key consideration for achieving a high-quality overall gain match. 1.4 The scope and contributions of a mismatch-compensated PFD/DAC synthesizer improves phase noise performance by reducing fractional and quantization noise. If quantization noise can be lowered significantly, it is possible that it will not have a noticeable impact on overall phase noise performance, and that intrinsic noise sources should become the area of design focus for continued bandwidth extension. By intrinsic noise, means noise sources that are inherent to any PLL, such as charge pump device noise, reference jitter, divider jitter, and VCO phase noise. This proposes techniques which allow low noise, high bandwidth, and fine resolution to be simultaneously achieved by a frequency synthesizer. Both intrinsic noise sources,